usual. Whoa, what the hell? Okay. So homework 8.1, number 7, is that right? All right, we've got the integral from 0 to pi over 51. 0 to pi over, what a lovely number that one is. X times the tangent squared of x dx. And so we have to come up with a way to break this apart. 17x, oops, I missed that, thank you. Yeah. $17x, it's supposed to be in there. Okay, so thinking about u's and dv's. So we usually want u to be something that's easy to differentiate, and dv something that's easy to integrate. And tangent squared's not ringing a bell as the derivatives of any trig functions, but secant squared is, right? Secant squared is the derivative of tangent. And so that could be useful. How do we change tangent into secant? I think it's secant squared plus 1. How does that sound? Anybody agree or disagree? Let's see, trig identities. It is secant squared minus 1. Okay, so I think that's what I would go for here. So we'll rewrite this as the integral, I'm going to ignore the boundaries for a moment, of x times the secant squared of 17x minus 1 dx. And so that will get broken into two integrals where I distribute the x. So I'll have to deal with the integral of x secant squared of 17x dx minus the integral of x dx. And I like this one better because I know the derivative of the secant squared is the tangent, which will help us out here. So new page, I'm just going to isolate that sucker right there. Switch colors. So now I want to consider what's the integral of x secant squared of x dx. And so we'll let u, I keep forgetting that, thank you. 17x dx. So let's let u equal x, so that du is equal to dx, and then dv can be the secant squared of 17x dx, and v then would be the tangent of x, because the derivative of tangent is secant squared. Oh, I keep forgetting that darn 17. What is wrong with me today? Lack of sleep, maybe. So it's going to be 17x, and then we're going to have to adjust, right, for the 1/17th because of the chain rule. Thank you. So rewriting that part, this blue integral, let's switch back to blue, is equal to uv, so x tangent of 17x over 17 minus the integral of v du. So that's going to be just tangent of 17x over 17 with respect to x. And does anybody remember the antiderivative for tangent? We did it in class one day by thinking of tangent as sine over cosine. And we had two different versions of it. Nope. Let's look it up. This is where those cheat sheets would come in handy. So I'm going to open up, let's see, what do I want to look at? The book, beginning of chapter 8. All right, and let's blow this sucker up. So again, your upcoming quiz is to make a table similar to this. And here they say tangent is the natural log of the absolute value of secant. When we were in class, we first derived it as the opposite of the natural log of cosine, and we were able to twist that into the natural log of the secant. Right. So that's one we can use there. I didn't prove number 14, but the proof of it is in the book. Why that works is this crazy little algebraic manipulation. And we really don't have time to prove everything. And so some stuff we just have to look up, which is fine. All right, so back over here, I think we're almost done with our antiderivative. This is going to evaluate as the opposite. I have that 1/17 hanging out, and then we're going to get the natural log of the absolute value of the secant of 17x. But the chain rule is always acting. So if I were to take the derivative of this natural log of the secant of 17x, I'm going to have the derivative of the natural log, I'm going to have the derivative of the secant and the derivative of 17x in there. And so I'm going to have another 1/17 from that. So a lot of times you got to double check. If you're not sure about that, you could do a regular U substitution on the 17x to see that that 1/17 is going to pop up every time we take an integral. All right, so I think we're almost done. One thing we left hanging back here is that guy, antiderivative of the opposite of x. So putting it all together, I think we have, let's try it in black. And you guys help me out on a new page, see if I can get it all together. That we started off with the integral of x tangent squared of 17x dx. And we still have to deal with the 0 to pi over 51. And we have that it's equal to x times the tangent of 17x over 17. And then we have a minus 1/17 squared times the natural log of the absolute value of the secant of 17x. And then we're going to have a minus x squared over 2. Did I get all of the pieces? Okay. And now we get to evaluate this fun guy between 0 and pi over 51. And one fun thing about doing calculus on this little screen here, most of the problems we do lately take like 3 of these little screens at least, which makes me miss a regular piece of paper where I can kind of fit most of it on one page. Anyway, all right, so what do we get? We get pi over 51. And then we also have a 17 down there in the denominator. And then we get the tangent of 17 pi over 51. That's a fascinating number. Minus, no extra constants there besides this one, 1/17 squared times the natural log, the absolute value of the secant of 17 pi over 51. And then we're going to get a pi squared over 51 squared times 2. What happens if I plug in 0? Tangent of 0? 0. Secant of 0 is 1 over the cosine of 0, which is 1, and the natural log of 1 is 0, and then 0 squared is 0. Whew, the lower bound is 0. What a relief. Okay, can we clean up any of this mess? My. 17 pi over 51 simplifies? Get out. Huh. Why am I not seeing that? 17 pi. Oh, right. 17 go. That's funny. 51, yeah, 5 plus 1 is 3, or 6, so 3 goes into it. Oh, man. You know what? That reminds me. 51 is the most common number under 100 mistaken as prime. And I just fell for it. I didn't think it was factorable. Okay, that was funny. All right, so this factors, thank you, as pi over 3. And just double check, tangent of pi over 3, let's see. Pi over 3 is 60 degrees. And the slope there is square root of 3. Is that right? Because that point right there is x is 1/2. And sine is square root of 3 over 2. Yeah, so tangent there is square root of 3, right? Okay. And this becomes the secant of pi over 3. And let's see. Cosine of pi over 3 is 1/2. So secant of pi over 3 is 2. Well, that's kind of nice. This does clean up quite a bit. Oh, fun. Let's get rid of this. Get most of it. Oh, come on. Get over here. I guess the eraser might have been easier. There you go. Okay, so where are we now? We have calculator time just about. Pi over 51 times 17, whatever that is, times, what do we say? That's the square root of 3, minus 1 over 17 squared times the natural log of 2. All right. And don't need the absolute value anymore. Natural log of 2 says e to what power is 2, which is not a nice number. I think it's 0.69-ish. And then we have minus pi squared over 51 squared times 2. Can't pull out a 17, can't pull out a 51, can't pull out a pi, can't pull out a square root of 3. Oh gosh, I keep forgetting 17 is 3 times 51. Okay, so we can pull out, everything's got a 17 squared in it, right? Does the online homework really want us to do that? Yeah, because 51 is, this is really 3 times 17 is 51 times 17. So there's a 17 squared. And 51 here, you could write that as 3 squared times 17 squared times 2. So everything has a 1 over 17 squared in it. So we can pull out a 1 over 17 squared. Big whoop. It's exciting. All right, so we have an answer. It kind of sort of simplifies with a 1 over 17 squared pulled out. And I'm assuming they wanted an exact answer here? Yeah, okay. And so then you very carefully type that in. Yeah. Good thing there weren't 50 of these, right? There were only, what, 14? Is that what I got it down to? Or did I get this one down to 12? I think it was the next 3 I couldn't get down below 14. There were too many cute ones to get it lower. All right, that was exciting. Oof. All right, next problem was number 9, is that what you said?
Yeah.
Okay. And that is the number right here?
Yeah.
Not part of the problem. Okay. So number 9 in the homework said to find the integral of x to the 9th times the square root of x to the 5th plus 5. Thank you, sir. With respect to x. Okay, so let's see. The first thing that comes to mind on this is that table version we did of e to the x and sine of x with polynomials, where we take the derivative of one over and over and the integral of the other over and over. That might help. Otherwise, let's see, are there any other algebraic tricks we can use here? X to the 5th plus 5 is not going to magically turn into any kind of perfect square. If I did a u substitution on that, a regular u substitution, I could turn that into the square root of u, but then I would get some craziness outside. So I'm just going to fiddle with this for a second before I try the table version. What if we did like a regular u substitution of x to the 5th plus 5? Then du would be 5x to the 4th dx, right? Now, unfortunately, I have an x to the 9th out there. Can we somehow get rid of that? So let's see, if we rewrite this, what if I say that's something like x to the 4th times x to the 5th times the square root of x squared plus 5 dx. Fifth, thank you, 5th. Then as far as my u stuff goes, I can put this right here. That's going to be the square root of u, right? Let's write it under here. So I'll have a square root of u. I've got 4x dx. I'm just missing the 5. So I think I can then have a 1/5 du. So I got rid of that and that and that. And x to the 5th, if you focus on this right here, is equal to u minus 5. Oh, so I wrote that badly. That implies x to the 5th is u minus 5, right? So then instead of the x to the 5th there, I can throw in a u minus 5. So I took the addition out of the square root. So integration by parts is powerful, but it's like a huge tool. It's like using a power circular saw when you only need a little hand saw to do something. Regular u substitutions are a little bit easier. Yeah, because then I can just rewrite this if I distribute that through and consider that u to the 1/2. Then this is going to give me 1/5 times the integral of u to the 1/2 times u, which is u to the 3/2, minus 5 u to the 1/2 du, and that's just the power rule for integrals. Okay, so that's one way to attack this problem. It's pretty straightforward from there. The other way is to consider integration by parts. So let's write this on another page and attack it from that angle. I think that's going to be way harder. So number 9 is the integral of x to the 9th times the square root of x to the 5th plus 5 dx. Sorry, that's supposed to be ending the square root. And this reminds me of a polynomial times e to the x or a polynomial times sine of x. The book introduced the technique of making a table where your U's come down in one column and your DV's go down in another. Now, the problem with that is you have to differentiate your polynomial, your power, all the way down to 0. So I would have a 9x to the 8th and a 72x to the 7th and I can't do this in my head, 9 times 8 times, oops, 7, wrong number. 9 times 8 times 7, x to the 6th, all the way down, and I'm going to have a 9 times 8 times 7, all the way down to 1, and then finally we'll get a 0 next. So we'll have 9, 8, 7, 6, 5, 4, 3, 2, 1, down to nothing. On the other side, we would have to, ooh, no, that's horrible. And we don't want to do that. Oh yeah, no, we don't. Integral of that is nasty. Yeah, this doesn't work because we don't have an antiderivative for that, right? If we check out our table, it's nothing we've seen yet. Where's our table? All the square root stuff are in the denominator. We don't have any square roots in the numerator yet. And remember, we tried working on that yesterday and filled up like 3 pages and weren't done yet? Okay, so that's not going to work. Is everyone with me why it's not going to work? Because we can't find dv, right? So then we might say, oh, well, let's just switch them. Let's let x to the 9 square root of x to the 5th plus 5 dx. Let's let u be the square root. What's du then? Well, du would be 1 over twice the square root, right? X to the 5th plus 5 times the derivative of x to the 5th plus 5, which is what, 5x to the 4th. Then dv would have to be the x to the 9th dx. And then v is going to be what? X to the 10th over 10. And then, yeah, because then my uv, okay, that's not too bad. Sorry, my uv is not too bad, but my udv, all of a sudden now I have an x to the 14th and I have that in the denominator. Oh boy, that got worse. So integration by parts on this one doesn't work. It turns out we need a regular use substitution is like the only way to do it. And you don't know until you try. So it looks like this is our only technique for that problem. Okay, let's take a look at that problem we started at the end of class yesterday. And so after I left you, I sat down to finish it and found myself in an infinite loop, which I hate when those happen, but they do. So we were trying to find an antiderivative, and we thought integration by parts might work. And we were able to rewrite this yesterday with an integration by parts of x times the square root. But now, think about the problem we just saw. Does that look reminiscent of the problem we just saw? We just made it worse. And so then I tried another integration by parts. And hey, I got a new piece I didn't have before. And this didn't look too bad. Okay. So then we were left with having to figure out, okay, what is an antiderivative for that? Okay, so what's an obvious u substitution? Well, wouldn't it be to let u be like 4x? And then that means we would have to integrate sine inverse, a hyperbolic sine inverse. But we haven't done that yet, have we? Okay, so let's see, what's the definition of the hyperbolic sine inverse? Anybody remember? That would be the reciprocal of the hyperbolic sine. Remember we had to solve with logarithms, and we ended up with the logarithm of, my recollection, I gotta look this up to double check, that the sine hyperbolic inverse of x is the natural log of the absolute value of x plus the square root of x squared plus 1. And I'm not sure if that definition is correct, so let's look it up. So if we look up, let's go to Wolfram alpha maybe, and say what is the arc sinh of x? Wikipedia would also tell us, and it's in our book in section 7.3 also. We could flip through the pages. And Wolfram alpha somewhere in here, after all this crazy stuff, will, oh, they do give a derivative there, or an antiderivative. I just want the definition, please. Oh, there it is right there. Yeah, I got it right. Okay. Well, here they have a note on the side that says in Wolfram alpha, where'd it go? Oh, they don't say it. Oh, it's down on this one here. Huh, they usually say it somewhere that for them, log means natural log. I mentioned that before. You got to double check the fine print of any computer algebra system because sometimes log is base 10, but sometimes it's natural log. And here they mean natural log. Yeah, so they do give us a version of it here, but notice that square root of x squared plus 1 pops up, which we still don't know how to do, which is related to the problem we started with. So let's just look at this for a second. Let's see, where am I? Over here. So if I want to let this be my dv, right? Basically, I have to be able to integrate this sucker, which means I have to integrate the natural log of the absolute value of x plus the square root of x squared plus 1. How the heck do we do that? This is a function within a function within a function, and we have no things outside of that function to act as a u substitution. So at the moment, we don't have any way to do this either. Okay. So what is commonly done is if you can't do this as u and that as dv, then you switch them. Let this sucker be dv and let this sucker be u. What that's going to do is reverse what we did right there. And then everything will cancel out and we'll get back to where we started. So if you change your u's and dv's mid-course in one that requires multiple iterations of integration by parts, you end up back where you started. So that's what I mean about an infinite loop. So I tried this 3 different ways last night and this morning, and every time I got stuck in an infinite loop. So I'm pretty sure integration by parts will not find this antiderivative, unlike I thought it would yesterday. And after trying it 3 times and failing 3 times. So if anybody can find a trick that I missed, you will definitely get extra credit. You have till the end of the term. Good luck. So I could not find a clever trick to do that. I bet somebody's written about it out there on the internet, but I was not going to look. So we hit about the limit of what we can do with integration by parts. It can solve a lot of problems, but it can't solve every problem. So problems that we need to solve now are going to involve us taking a closer look at trigonometric functions. So we're going to go back and look at trigonometric functions. Trig functions. And so we're going to need trig identities to do this. So we're jumping into section 8.2 now. So we can do some pretty powerful things with integration by parts, but we still can't do everything. Integrals that are going to be useful to know that the integral of the cosine of x we know the integral of the, how about secant squared? What's that one? Tangent, yeah, tangent. Yeah, so all the derivative formulas we learned are going to be super helpful. And then there's a few new ones, like in section 7.1, they go over how to find the integral of the secant of x on its own. Of x, oops. And what they do is they do this little trick where they multiply top and bottom by secant plus tangent. right? So you multiply by secant plus tangent over secant plus tangent, and in the end, you're able to use a u substitution and prove that this is equal to the natural log of the absolute value of the secant of x plus the tangent of x. If you want the details, please look in section 7.1, and then you still have that pesky plus c. So we're accumulating more and more ways to deal with sine and cosine. And so now we're just going to throw them together in interesting mixes and see what happens. So for example, what if we had the integral of the cosine squared of x times the sine of x dx? How could we cope with that? Well, what comes to mind here is the derivative of the cosine is the opposite of the sine. So I think I have a regular u substitution living in front of me here. And so if we let u equal cosine, let's see, where's my colors? There you are. Then du is the opposite of the sine of x dx, and I have my sine of x. The only thing I'm missing is my opposite. And we can multiply both sides by -1 here. And so we get sine of x dx is the opposite of du. So we can rewrite this integral with this substitution as the integral of opposite of u squared du. So that gives me the opposite of u cubed over 3 plus c. U is really the cosine, so this is the opposite of the cosine cubed of x over 3 plus c. And let's just think about that for a moment. This is a chain rule as a derivative if I take it in reverse, and the derivative of something cubed is something squared, right? The 3 is going to come down in front and cancel the 3 in the bottom. Chain rule says you then have to also multiply by the derivative of your base. Derivative of cosine is what? Negative sine, right, which gives us that sign up there and cancels our negative, and so yeah, it looks like that worked okay. What if we didn't have the sign to help us out? U substitution is not going to work here because the du is missing. So then we need another trick. Well, it turns out you guys have lots of tricks.
A trig identity?
Like a trig identity, yeah. So if we look at our list of trig identities here, I prefer, instead of the half angle, I usually use the double angle, but we could use a half angle. So here we have a half angle formula that says the cosine squared is really 1 plus the cosine of 2u all over 2. That solves our problem right there. So trig identity says this is equal to the integral of 1 plus the cosine of 2x over 2 dx. Now I can pull out that 1/2. And so then I just have to integrate 1 and cosine of 2x with respect to x. Not too bad. I'm going to have a 1/2, and then integral of 1, well, that's just x. An antiderivative for cosine is the sine, but the 2x is that pesky chain rule. We don't have a 2 times the cosine here, so we have to compensate down here with a 1/2 to satisfy the chain rule in reverse. And then I can put my plus c. So differentiating this bottom line should take me back to the half angle formula. The half angle formula takes me back to cosine squared. Okay. So if there's even powers of cosine and not a corresponding sine to help deal with that, that's one way to handle it. some other interesting predicaments we might get into with sine and cosine. What if we have a bigger power of sine or cosine in there? So let's take cosine to the 4th power of x. Now, if the sine was sitting next to us again, no problem, right? We just use substitution, it's cake, it's no problem. We don't have, oh, what's that?
What if you treat it like cosine squared times cosine squared?
Yeah, this is the square of cosine squared, yeah. So we can rewrite this and say, hey, this is just the integral of the cosine squared, and we have the half angle formula, we can work on that. So that's going to give us 1 plus cosine of 2x over 2 all squared dx. And we can't substitute our way out of squaring that because there's no du hanging around if we have u be something related to the cosine of 2x. So we got to multiply this sucker by itself. And so I don't have much of a choice to say I'm going to have a 1/2 squared as a constant, and then I have 1 plus cosine of 2x times 1 plus cosine of 2x. So sometimes algebra is our only means to evaluate integrals to get them somewhere we can handle. And we'll have to distribute each term in the first by each term in the second, and then integrate that. So let's write that out. So we have now 1/4 times the integral of 1. We'll get 2 cosine of 2x's. And then we'll get cosine squared of 2x, all with respect to x. And we have another predicament, another cosine squared. What do we do with that? We use our half angle formula again, and now notice they use a u in there, which helps me think about this one here. They say the cosine squared of u is 1 plus cosine of 2u. Now our u here happens to be a 2x, so I'm going to get a 2 times 2x when I apply that. So we're almost ready to actually find some antiderivatives here. So this is going to be rewritten as 1/4 times the integral. 1, that's no problem. 2 cosine of 2x, that's no problem. And then that cosine squared is going to be rewritten as 1 plus the cosine of 4x over 2. And now I'm finally at a point where I can come up with an antiderivative. So let's do that. So let's see, we're going to have that 1/4 hanging out. Antiderivative of 1 is x. Antiderivative for the twice the cosine of 2x. Well, the derivative of the sine is the cosine, so that's going to be positive. So yeah, careful. That's something that I make a mistake about all the time. And we did have the 2, the chain rule requires outside there, so we're good. It's just sine of x, a sine of 2x, excuse me. Over here, I have a plus 1/2. So I'm going to call that a 1/2 x. And then I also have there, so I'm thinking about this as 1/2 plus 1/2 cosine of 4x. The chain rule would require there be a 4 cosine of 4x there, but I don't have that 4, so I have to compensate with a 1/4. So I'm going to have a plus 1/2 times 1/4 times the sine of 4x. Close that, and I still have a plus c because I didn't have boundaries. This is an indefinite integral. And this cleans up a little bit. I could clean it up a lot if I messed around with double angles and so on. So we're going to get, I'm just going to leave that 1/4 out front. X plus 1/2 x is 3/2 x, plus the sine of 2x, plus 1/8 the sine of 4x. And then we have our plus c hanging out. And we could probably take this a little farther if we applied the double angle formula of sine multiple times each and break it down even further, but it's not going to be too much compared to that. Anybody remember the double angle formula for sine? Two times the cosine times the sine. Yeah, so if we do that, then we don't have just sines anymore, we have sines and cosines, and the question is, does that really make it better? I don't know. So I think this is far enough. Only way to double check it is to take the derivative of it and see if it cleans way back up to what you have here, cosine to the 4th of x. One thing about these kinds of derivatives, since there's different identities that can be applied in different orders, you will often get different looking answers in the end. So it's possible somebody else applied a slightly different version of the trig identities, and they'll get an answer that looks totally different, but they can be equal. And that's going to happen a lot. This might happen in the online homework. So if you think you have an answer that's right, but the homework doesn't like it, message me and send it to me so I can take a look at it. And we can probably find a way with identities to show, yeah, yours is equivalent. It's just that pesky plus C there that makes other things available to us. An example of something like that, we looked at the integral of the secant of x the other day, and our first jab at that was that it was the opposite of the natural log of the absolute value of the cosine plus c. But just with a little bit of algebra and natural log properties, we were able to rewrite that as the natural log of the absolute value of the, oh, am I doing that right? Secant squared is tangent. Secant is 1/cosine. Now I forgot which one I mean. Let's see. Where's the book? Tangent, not secant. That's right. Yeah, so if this were tangent here, sorry, we got that version. The other version is this one right here. So you can have two different looking answers that are equivalent. Okay, and that happens a lot with trigonometric functions. So I'm going to stop here. Section 8.2, is that where we are now? Is all about playing around with powers of sine, cosine, tangent, secant. Mostly you're going to apply a lot of trig identities and try and come up with an antiderivative. So we'll touch on these some more on Monday, and then we'll look at a slightly different way of using trig functions, which is called trig substitution, where we use right triangles to rewrite integrals involving square roots. And then I did finish grading your tests. No, that's a lie. I finished correcting them. I got to finish assigning grades to them. And so I will post grades hopefully by tomorrow. And then if you're, thank you very much. And I will, as soon as I'm done grading, I'll post my answer key too, so you can take a look at that. And for those distance ed students like Gerald, I will email you your corrected test. If anybody else can't wait till Monday for it, then let me know and I can scan it and email it.
Gary?
Yeah, hey Darren.
I was looking at the grades and I saw that the exam corrections 1 still hasn't been graded yet.
I've graded them, I haven't plugged them in. I'll plug that into Canvas soon.
Just making sure.
Yeah.